Okay, so let's get started. We're going to be taking a look at how to set up and configure our target Lambda table in our model fuel equation mode with our Link G5 and G4X systems. Now, let's first go from our basics page and jump over here to fuel. In fuel, we find that we have our main fuel table. We know that's the volumetric efficiency table. We discussed that pretty heavily in the last training module. We understand how to scale these breakpoint axes for MGP or manifold gauge pressure, engine load, engine speed, as well as the values in the table should be in a certain range. At idle, anywhere between 40 to 50 typically, sometimes as high as 60. Part throttle, they should be somewhere in the range of 60 to 80. Full throttle, naturally aspirated, anywhere between 80 to 100. And then as we get into positive manifold pressure, they can go up as high as about 120, 140. They shouldn't go much higher than that. The limit of the table values is 150. Now, when we're talking about doing our calibrating and tuning of our actual volumetric efficiency table, one of the first things we have to set in our base map is what we want to run our engine at in terms of our fueling mixture. We don't want to run it too rich or too lean. We want to make sure that things are appropriate because we calibrate our main VE table around our target Lambda table here. These are directly in connection with each other. And in fact, we've talked about our airflow modeling and fuel modeling. It's going to be fuel mass is equal to air mass divided by target air fuel. We know that the air mass comes from portions of the parameters we factor in here. So under the configuration of fuel main settings, this is going to be accounting for things like engine displacement, number of cylinders. We have air density that's factored in. It's using air temp and coolant temp readings. And then we have our volumetric efficiency percentage values in here. This is going to account for the cylinder filling of the engine. So essentially, we're calibrating things, we can determine the air mass. If we know the air mass, then we need to know what the target air fuel is going to be. The target air fuel comes from our target Lambda table, as well as knowing our fuel stoich that we're working with. So this represents the actual fuel that we're dealing with. 14.7 assumes pure petrol fuel, so there's no ethanol blended in our fuel. So we multiply fuel stoich by our table Lambda values here, and that gets us a target air fuel. So we know air mass, we divide that by target air fuel, we get a fuel mass. We can convert that into injector pulse width, knowing the injector flow, the latency, the short pulse width data. That gives us the actual pulse width. So it's a pretty simple equation. But we have to make sure that our target air fuel is essentially decided ahead of time. We want to make sure that as we're calibrating and tuning our engine, calibrating and tuning our volumetric efficiency table here, again, that these values make sense for where we're running our engine at. We don't want to run a lean mixture if we're getting into boost. Likewise, we don't want to run a rich mixture as we're idling and running our engine in the idle area. So we want to do things that make sense. So let's go into the table here and talk about what we have going on here. So in our target Lambda table, let's first discuss the breakpoints and the scaling. We want to make sure that's appropriate for the engine that we're tuning, meaning we don't necessarily have to go in and have positive MGP or manifold gauge pressure. Let's say if we're naturally aspirated, we would only be hitting approximately 0 MGP. We wouldn't be going up here to 20, 40, 60 MGP. That's going to be getting into boost. Wouldn't make sense to set up our target Lambda table for getting into boost if we're actually not getting up into that range. Likewise, we don't want to scale the table out just at 0 if we're getting into positive manifold pressure. We want to make sure we're accounting for MGP going into higher values here. The same is going to go for engine speed. We want this table to be reasonable so that it's accounting for most, if not all, of the engine's operation RPM range when we're scaling and setting this up. Let's go and take a look at how we can do that breakpoint scaling real quick. So if we click on the table here and click X, this allows us to go in and configure the axes for both the Y-axis and the X-axis. So the X-axis is engine speed, the Y-axis is our load axes based on MGP. Now, a couple choices here. When we're talking about our Y-axis, when we're looking at our volumetric efficiency table, we talked about this in the last training module, MGP or manifold gauge pressure is kind of a little bit of an odd parameter to work with if you're used to coming from other systems such as Haltech, AEM, a lot of the other plug-and-play systems or other universal standalone systems do not include or do not work with MGP or manifold gauge pressure. This is the comparison between our baro and our map pressure. In fact, it's map pressure subtracted from the baro pressure. So it's map minus baro gives us the actual MGP reading. Now, MGP is useful in our model equation mode here, our model mode, taking a look at our load axes, because it directly recalculates and recalibrates our fueling based on changes in elevation. So it's baked into our fueling as we're delivering things, as we're calculating things and delivering the fueling to the engine. It's directly baked into the axes. We don't have to worry about having a baropressure compensation. When we're talking about the...
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.